you have a ketone here, we add a base at the outside, and should put it all together. I think you should cross the numbers away. And of course, the number 2 there. But anyway, the thing is that the dioxide will take these protons away, you're going to form an enolate, right? The main point of this question is, you form an enolate, then you're going to react into the key ester here. But you see this ester is not just ester here, but it's conjugate ester, alpha beta unsaturated ester. That's just where we talked about electrophilic center, which is electron deficient center, can be the carbonyl, but also the beta carbon there. And then enolate, being a soft nucleophile, it rather attack beta positions. But I just want to show you what could be the wrong answer first. If you just don't pay attention to this double bond here, then most likely you're going to take this enolate, making attach to the carbonyl of the ester, you get the tetrahedral intermediates. Then when you make the ethoxide kick out by making a carbonyl, you could potentially have that as a product. But you know, I'm going to say that that is not the major product, because the enolate is a soft nucleophile. It rather wants to attack the beta positions for the micro additions. When that attack, this goes here, make a double bonds here, this goes up, a carboxyl group there. And then this will come back, making a carbonyl, and this will become the proton. Then you get the conjugate addition. This is a beta position that where this nucleophile makes an attack. So that is a micronation product. I suggest this is what happened, not that, because the enolate is a soft nucleophile. So you got to pay attention what is getting reacted. If this one reacted with the Grignard, Grignard doesn't do the microaddition. Grignards attack the carbonyl directly because Grignards are considered very hard nucleophile. So you get this thing after reacting with the Grignards because of the alcohol. But if you're using a soft nucleophile like this enolate, diethylcuprate, thiol, all those things will attack the beta positions, the micro positions. So that is something that you need to pay attention in this question. All right. The next one. The question kind of already revealing what type of reaction you need to consider. One ring with a double bond there and a carbonyl here, like ketone, becomes a two fused bicyclic. So this is actually the ring annulation. You only need one reaction so far for doing this thing, but it's a ring annulation. So this is basically, you can easily recognize it. The question is, can you recognize which molecule you have to react with properly? So that's the question. So you need to recognize where in the product corresponding to the starting 6-member ring. Is that 6-member ring going to be this one, or is this 6-member ring going to be that one? Which one of that is coming from the original starting ketone? So if you recognize that, then finding the other part is a kind of very straightforward. But the first part is hard, right? You've got to remember the mechanism to follow that. What happened was, this enolate will make an attack microaddition, and then that will attack back. You're going to have this hydroxyl group form, and then you're going to get the double bonds created like this. So that is coming from this carbonyl losing a proton after another reactions. So this portion, that part, is one that came from the original cyclohexyl ketone. So this part is this one. And then that portion, that's the one that you need to react to for the enolate. So that's something that I want you to be able to recognize. So what should happen? You need to make an enolate by taking these protons away. Let's say you can use sodium ethoxide here. They will take these protons away. You're going to get the enolate formed this way. And then that's the reason why we did the analysis. We're going to find out which unsaturated ketone that we need to use. That is basically alpha beta unsaturated ketone that we need to make a microaddition, right? And then the carbonyl is here. It's not just ending here because we have an ethyl groups. So it's an ethyl groups down there. So that is what we need to react to. First step is a microaddition. This annulate will make an attack. This will go make a double bonds here. This make an a carboxyl groups. That will basically pick up the proton. Then usually it's going to go back to keton again, right? This will come back, pick the protons. So it's going to go back to keton. Then this dark side will pick up that proton here. It's not going to pick up from that proton because if you pick up that proton here, this proton is going to go back. I mean, it will never all the way back, but this is not going to be anything. So it can be back and forth, nothing really happening. But when it picks up this proton on the other side of the keton, then what happens is you are making different phenolate, that phenolate. And then that phenolate makes an attack to this keton as an outdoor reaction, right? And this will basically make an OH here, and then now you've got the green close just like that. You've got the carbonyl in the right place. These methyl groups hanging around there, everything right, except this hydroxyl group has to go. But that can go in acidic water in the end by just putting in the water, and it will be going as double bonds. So you create that. So reannulation question. It's not difficult to recognize it. If you see that one way because of tuning, that's what the green by anything, right? So that is really showing what it is. But you got to find out the white components of the reagents. So for that, you need to know the intent. Okay. I mean, it can happen in the basic condition too. In the case of basic condition, the base, this sodium hydroxide comes pick these protons up, make a double bond, pick the hydroxide out, either way, double bonds. So this is the basic of obviously.